Global Finance, Topic 19, Global Portfolio Optimization, Computing N-Asset Portfolio Risk and Return. Copyright Lou Gaddis. In this topic, we'll talk about the process of portfolio construction and optimization, compute the mean, volatility, and Sharpe ratios for many asset portfolios, and show how you can combine risky assets and risk-free assets to make optimal portfolios. So we'll start with the data I've collected from 2003 to 2010 and some estimates I've made. So I'm going to use three asset classes: U.S. equity markets, developed equity markets, EFA, and emerging markets, we'll call EMA. I have estimates of standard deviation for those three asset classes, estimates of expected return for those three asset classes. I've collected a correlation matrix, so you can see the correlation between US and EFA, I'll assume is 0.6, US and EMA 0.5, and EMA and EFA 0.5. You can see the major diagonal correlation matrix are 1, as assets are perfectly correlated with themselves. And on a correlation matrix, you can see that these values are just repeated. And I'm going to look at creating a portfolio that's 50% invested in US, 40% in EFA, 10% in EMA. We'll first calculate the portfolio return. The portfolio return for an N-asset portfolio is the sum from I equal 1 to N WI RI. So the sum tells us that we're going to have N number of assets. So say we have 2 assets. It's the sum from 1 to 2 of the weight of asset I times the return of asset I. So the sum works like this. The sum works like a counter. The I is the counter. We're going to take it from 1 to 2. So you can set I equal to a value of 1, plug in WI-RI, W1-R1, and then set I equal to 2, and you get W2-R2, and then we're going to sum it up. The sum of a 2-asset portfolio is W1-R1 plus W2-R2. If there were 3 assets, I would just have a third row, and I'd sum up W3-R3. So if we're looking for the expected return of this 3-asset portfolio, I would simply take my assets 1, 2, and 3, and I'd plug in WI-RI. So it would just be the sum of these 3 products, 50% of 9%, 40% of 9.5%, and 10% of 10, which turns out to be 9.3%. Now we're going to calculate the standard deviation. So we think that, or we've estimated that the portfolio has a 9.3% return. The question is, what is the standard deviation of the portfolio? It is not going to be the weighted average, where I would just say the standard deviations times the weights. There's only a special case when that's true. And that case is when these assets are perfectly correlated. When these assets are perfectly correlated, there's no diversification benefit by putting them together. Therefore, the risk is simply the weighted average standard deviation. However, if these assets are not perfectly correlated, we have to account for how these assets move in conjunction with themselves. So we have to look at each asset, pair them together, and see if there's diversification benefit by putting them together. The formula for calculating the variance of an N-asset portfolio is the double sum I equal 1 to N, J equal 1 to N, WI, WJ, sigma IJ. So again, these are our weights, and what we're looking at is all the assets paired together. So there's going to be 2 weights, and then this last term, sigma IJ, is the covariance between asset I and asset J. Now covariance is similar to correlation. Covariance between 2 assets is the correlation, which talks about the direction of their movements. 1 being they move perfectly together, and -1 meaning they move perfectly apart in some sense. But it's also scaled by how big the movements are. So you can think of covariance as correlation, also with a kind of a scaling effect of how big the moves are. So a positive covariance means that the correlations are positive, they move together. And if it's larger, that means those assets are more volatile. Now the double sum is just a way of trying to figure out all the pairwise combinations of the assets so we can look at the combinations. So let's show you how to use that. So double sum I and j, you have two counters I and j. And then what you're going to do is you're going to set the first counter I equal to 1 and set j equal to 1. And then we're going to plug in wi, wj, sigma ij, which is w1, w1, sigma 1, 1, which you can rewrite as w1 squared, the weight in the first asset squared, times sigma 1 squared. And you can think of that as, well, that is the variance of asset 1. Actually, the covariance between one asset and itself, by definition, is the variance of the asset. And then we have set I equal to 1 and j equal to 1, then we'll increment j. Set I equal to 1, j equal to 2, then plug in 1, 2. So you have W1, W2, covariance 1, 2. All right, j has run its course, then we'll set I equal to 2, and then we'll set j equal to 1 and 2. When I is 2 and j is 1, we have 2 and 1, so another covariance term. And then when I and j are 2, you have W2 squared, sigma 2 squared. So what you see is by using this method of ensuring that you figure out all the pairwise combinations of assets, you effectively account for the variance of each asset. So we have variance of 1 and variance of 2. And we look at the combinations or the covariances between assets. These are identical, actually, so there's 2 of these terms. So when we sum them up, you can see here's the W1 squared, sigma 1 squared. That's that term. Here's the W2 sigma 2 squared. That's that term. So that accounts for the 2 variance terms. And then there's 2 of these terms, 2 of these covariance terms. Now, if there's 3 assets, again, we're looking at pairwise combinations. So when you have 3 assets, you have 9 pairwise combinations. 1 with 1, 2 and 3, 2 with 1, 2 and 3, and 3 with 1, 2 and 3. So I'd set I equal to 1, j equal to 1, W1 squared, sigma 1 squared, and then j equal to 2 and 3. And you get 2 more covariance terms. And then you set I equal to 2 and j equal to 1, 2, and 3. Plug in your terms. And then set I equal to 3, j equal to 1, 2, and 3. So whenever you have 3 assets, you're going to have 9 pairwise combinations. If you have 10 assets, you're going to have 100 pairwise combinations. Again, we would just add up these 9 numbers, and the sum of those 9 numbers would be the variance of the portfolio. And what you'll see is there's 3 variance terms and 6 covariance terms. An easier way of looking at the possible combinations of assets is to set up a covariance matrix. So if we have assets 1, 2, and 3, 1, 2, and 3, instead of putting it in a table of 9 rows, we can set up a 3 by 3 matrix. So here's 1 with 1, 1 with 2, 1 with 3, 2 with 1, 2 with 2, 2 with 3, 3 with 1, 3 with 2, 3 with 3. And what you see with this covariance matrix is the major diagonal are your variance terms. The off diagonals are your covariance terms, and you can see that these actually are repeated. The covariance between 2 and 1 is the same as 1 with 2, 3 with 1 is 1 with 3, and 3 with 2 is 2 with 3. We usually like to write things like this in finance using a matrix because it's a lot easier to use, and later you could use, say, matrix algebra to solve these problems. So let's get back to our problem. We've estimated standard deviations for the 3 assets. Expected returns of the 3 assets. We calculated the weighted average return. We're plugging in weights for our portfolio. We have a correlation matrix, and then we're going to build a covariance matrix. Since each covariance term is a correlation times 2 standard deviations, you can see that, say, the covariance between IFA and US is going to be the correlation between IFA and US times the standard deviation of IFA and the standard deviation of US. So this number right here would be the correlation between the two, USA and IFA, times the US standard deviation times the IFA standard deviation. So we can complete this covariance matrix by filling in the other terms. The covariance between US and EMA will be the correlation between US and EMA times the standard deviation of US and EMA. and that would be 0.016. And if we're looking for, say, the covariance term here, it would just be the correlation between EMA and EMA times the standard deviation of EMA times the standard deviation of EMA, which is 0.04. Or you can also know that the covariance between EMA and EMA is by definition the variance of EMA, so it's just be sigma squared, 0.2 times 0.2. And then you could repeat these numbers up here. Whoops, 0.01632. That's 0.016, 0.017. And if we go a couple slides ahead, you can see the full covariance matrix. Now, what we said is the formula, variance of a portfolio, is the double sum Wi, Wj, sigma ij. A way of computing that for three assets is to set up a 3x3 matrix. So you have your covariance matrix here. And what you see is you just have to plug in the weights for each covariance asset pair. So that we can create another matrix, I'll call it the variance calculation matrix, that has 9 terms. And if we can calculate these 9 numbers, we can sum them up and get the variance of the portfolio. So in Excel, I can take a covariance matrix and a vector of weights, combine them, and create this variance calculation matrix. So for example, if we're looking at, say, this number, the term which is EM with US, I would just take the EM covariance term times the US weight and the EM weight, and that product of those three numbers would be 0.008. So for example, if we're looking for this value here, the term that has US and IFA, I could take the covariance, and since this is US and IFA, I'll take US and IFA weights. That will give me 0.00326. Or if I'm looking at EMA and EMA, I could take the covariance term times the weight of EMA times the weight of EMA. Which would be 0.0004. So then you can fill in this last matrix, and you have all your terms. So again, from the beginning, we created estimates of standard deviations, returns, guessed some weights in here, got a correlation matrix. From the standard deviations and correlation matrix, we calculated a covariance matrix. From the covariance matrix and the vector of weights, we calculated this last variance calculation matrix. If we sum up these 9 numbers, so if I take the sum of these 9 numbers here, take the square root of it, that'll give me the standard deviation of the portfolio. So this portfolio 50-40-10 has a 9.3% mean and a 14.46 standard deviation. I graphed it, and that portfolio is right here. Here's my US, my IFA, and my EMA. So one question I asked is, if you could borrow and lend, or borrow and invest at 2%, is this portfolio superior than these other 3 assets? Or is it not superior, or can you not determine it? Well, in this case, if you can borrow and invest at 2%, I can combine that portfolio with the risk-free asset, either investing or borrowing, and get along this line. You can see it's clearly better than every other portfolio combination. So I'd say yes, this portfolio is better. Now if I did not say you could borrow and lend at risk-free rates, then you can say no, it's not clearly better. Because for example, you can look at the portfolio and compare it to EMA. Compared to EMA, this portfolio has lower risk and lower return. So it would just be a choice of whether I want a lower or higher risk and return. But once you have a risk-free asset, it's clear that this is the only portfolio you want to choose among these 4. However, we can see if we can do better than this 50-40-10, which gives us 930 mean and 1446 standard deviation. And what I'll do is I'll use solver. In solver, I'll ask solver to minimize portfolio standard deviation by changing these three weights and set the mean equal to 9.3% and make sure the weights sum up to 100%. When I run solver, what solver will do is it'll randomly select values of the three weights until it finds a global minimum. And it did. It found a portfolio that has the same mean as 50-40-10, but a little bit lower risk. Right? The last one was 1446. This one is 1442. So you can see this is clearly a better portfolio, and it would dominate the 50-40-10. So 54-32-14 would clearly dominate 50-40-10. Same return, less risk. Now we call that an efficient portfolio. Efficient in the sense it has the minimum standard deviation for a given level of return. So for a 9.3% return, this is the portfolio that gives the lowest risk. And then I can run solver 4 different times to get 4 more efficient portfolios. And if I plot those, I call that the envelope. The efficient set of portfolios would be the points of the envelope above the minimum variance portfolio, because we would never want to invest on this part of the envelope, because I'd rather be up here. So this is our efficient frontier, this part of the envelope. So the last thing, if there were no risk-free asset, I would just pick an asset on this envelope. Again, so we said the whole line is the envelope. The efficient frontier would be this part of the envelope, because I wouldn't want to invest here. So if there's no risk-free asset, I would just pick one of these points based on my risk preferences. So if I want a lot of risk, I would say pick one of these portfolios, which is mainly emerging market. If I wanted a safer portfolio, I'd probably pick something like this, which is mainly US markets, the safer market. However, if there is a risk-free asset, there is only one portfolio on this line you'd actually want. So if I change the scale of this to get me down to, say, a 2% risk-free rate, we would notice there's only really one portfolio that you'd want to hold. Right? I wouldn't want to combine, say, risk-free assets and this portfolio. I would rather combine risk-free assets with this envelope portfolio. So we need to find what envelope portfolio or efficient portfolio is a tangency, has the highest slope with a line extending from the risk-free rate. So we call the slope of a line going from the risk-free rate to a risky portfolio the Sharpe ratio. So what I'll do is in Excel, I'll set up a formula. I'll say the portfolio Sharpe is going to be the mean return minus the risk-free rate over the standard deviation of the portfolio. I'll calculate that number, and then in solver I'll maximize that by changing these weights, making sure I have 100% invested. And I also add a constraint to make sure there's no negative weights. When I do that, I come up with one portfolio. This is the portfolio that is the tangency, the highest slope on my envelope. And now that is the only one I'll actually invest in. So if I want a little bit of risk, I'll combine this portfolio, which is 38% US, 37% IFA, 26% EMA, provides a 944 return and 1448 vol. If I want a little bit of risk, I'll combine that portfolio with mostly treasuries, say 90% treasuries and 10% of that, and I'll get to a point right here. So that would be a safe portfolio. Or I can get a riskier portfolio here that might be, say, 90% of this risky portfolio and 10% treasuries. Or even if I can borrow at that rate, I could borrow money, invest my equity plus the borrowed money, and reach points out here. So the last step in the portfolio optimization process is to pick a level of return and figure out the risk, or pick level of risk and figure out what level of return you get investing on this capital allocation line. So the last two problems we'll just show are the case of picking a point on a line. So the first one says that we're investing in this portfolio has a Sharpe of 51.4, and we want a 10% standard deviation. What is the expected return? It looks like it's around 7%, but we can calculate it. We can use the equation of the line, capital allocation line. Return on portfolio on that line is the risk-free rate plus the Sharpe times the standard deviation. So we can say that it's going to be 2% plus our Sharpe from down here times our desired standard deviation, and you get a 7.14% return. And that portfolio is right here. And this is about the halfway mark on the portfolio, so I say this portfolio is roughly 60% of the risky portfolio and roughly, say, 40% of treasuries, since it's more on the way to the risky side here. And that's how I build that portfolio. And you can calculate that if you go back to the last topic and see how to calculate the exact weights. However, if an investor wants to specify a return requirement, you can figure out what the risk is. So it looks like it's going to be around 5%, but let's do the calculation. We're going to take our CAL and rearrange it and solve for standard deviation. So our standard deviation would be the return on the portfolio minus the risk-free rate over the Sharpe. So if we want a 5% return minus our 2% standard deviation divided by our Sharpe, we get a 5.84% vol. So it must be a little bit farther out here. And that's how I get that portfolio. And if I look at this portfolio, it looks like it's mostly treasuries and a little bit of risky portfolio. So this topic, we learned the process of portfolio construction and optimization, how to compute an asset mean and volatility and Sharpe ratios, and how to combine optimal risky portfolios and risk-free assets to get a tangency point on the CAL.